Hello friends, and welcome to a video lecture on topic R1.1 Measuring Enthalpy Changes. So much thermodynamics. Our guiding question for today: what can be deduced from the temperature change that accompanies chemical or physical change? Our understandings are here if you want to pause the video and read them. And our objectives: we're going to look at so much vocabulary. We're going to talk about endothermic and exothermic reactions. We're going to analyze some energy profiles. We're going to talk about the relationship between enthalpy of reaction and then the stability of reactants and products. We're going to wrap up with so many calculations. If you don't already have a calculator nearby, pause the video, go grab one. You're also going to want your data booklets. But before we dive into all of those details, let's talk for a little bit about some of the context around energy transfer. This is going to feel super commonsensical, but it's important to think about just to make sure that everything else that comes later makes sense. This system that we are going to talk about for the rest of this lecture is all about the contents of a flask or a beaker or a test tube. It's where the reaction is occurring. Sometimes we don't even include the beaker or the flask or the test tube. Sometimes the system is just the chemicals in which the reaction is occurring. And then outside the system is the surroundings. The combination of the system and the surroundings is the whole entire universe. What's kind of cool about the system is that sometimes energy will be propagated by the reaction, and that energy will be transferred to the surroundings. And sometimes in lab, I'm going to ask you to touch a test tube or a flask to notice temperature changes. Your hand then becomes part of the surroundings, and energy will be transferred from the system to your hand, or sometimes from your hand back to the system, which is pretty fun to think about. Energy transfer can be heat. We're going to talk a lot about heat, this transfer of thermal energy from a warmer body to a cooler body. But energy transfer could also be light or sound or electricity, lots of things. We're going to focus mostly on temperature changes and this idea of heat. Most of the systems that we work with in the lab are open systems. Our open systems allow for mass transfers and also heat transfers. This test tube is open. Let's say that I had some hydrochloric acid and I dropped in a piece of magnesium. The reaction that is going to occur between the magnesium and the hydrochloric acid is going to propagate some hydrogen gas bubbles. If my test tube is open, that hydrogen gas can dissipate out into the surroundings, which is a mass transfer. The mass of those hydrogen atoms can get out of the system and into the surroundings. This reaction also propagates some heat, and that heat can be transferred also from the system out to the surroundings. A closed system, in this case, we're going to put a rubber stopper on top of our test tube. I still have that hydrochloric acid. Maybe I dropped in some magnesium before I put the rubber stopper on. Hydrogen gas is still going to be propagated, but now it is going to be captured, contained inside the system because the system is closed. However, we're still going to feel temperature changes because heat propagated by the reaction is going to be able to transfer out into the surroundings of the system. Isolated systems, in these cases, we're working really hard to insulate our system so that neither matter nor heat can get in or out. And as promised, oodles of vocabulary, including that word heat that I just used quite a few times. Notice that these vocabulary words here, some of them we use in common everyday language, but the definition here in chemistry and thermodynamics is a little bit different from in common everyday language. Just pay attention to those super important differences. Temperature is a measure of kinetic energy, average kinetic energy of the particles within a substance. Kinetic energy is all about the energy of movement. Gases move a lot, liquids move a little bit less. Solids, those particles sit and they wiggle and they jiggle, so they're still moving, even though they don't move quite as much as gases. Now, when all motion stops, including the movement of those electrons in atoms, then we have reached absolute zero, which is a super cool idea that we can't actually get to in real life. But if we could, that absolute zero would be literally zero kinetic energy, zero motion, 0 Kelvin, negative 273.15 degrees Celsius. We're going to talk a lot about temperature change in thermodynamics. We're going to use the Greek letter delta to represent the idea of change. And to calculate the change in temperature, we're going to find a final temperature, subtract from it initial temperature. That's going to give us change in temperature. For example, if I had some water that was at 10 degrees Celsius and I warmed it up until the final temperature was 20 degrees Celsius, the difference would be a positive 10 degrees Celsius, which meant that the temperature increased by 10 degrees. Heat. Heat in common everyday language is not the same as it is here in thermodynamics. Heat is energy transferred from a warmer body to a cooler body. It is thermal energy. But in order for us to have heat, we have to have a temperature gradient. There has to be a warmer body and a cooler body. You can't just talk about, whoa, today there's a lot of heat. That heat doesn't exist unless there is some thermal energy being transferred from a warmer body to a cooler body. Perhaps the atmosphere is warmer than our human bodies, and then there is some heat because the transfer of that thermal energy to us from the atmosphere is happening. But if I don't have things of different temperatures, then there is no heat. How can that heat be transferred from a warmer body to a cooler body? We've got conduction, which requires things to be touching. Convection, this is where we have our source of thermal energy that warms things up, and those warmer things rise, which is going to take with it some of that thermal energy. And then radiation, this is literally just electromagnetic infrared radiation, those heat waves, which are taking thermal energy from a warmer body, perhaps the stovetop, to a cooler body, perhaps the air. Related to heat is enthalpy. Enthalpy is H and heat is Q. Heat can also be capital Q. A chemist named Rudolf Clausius said, I think we should call heat Q for quantity of heat. So Q for quantity of heat. Lowercase q and capital Q, both of those work for heat. Enthalpy is H. Enthalpy is the heat content of a system, which we can't actually measure because in order for us to measure it, it has to be transferred, which is weird. So most of the time we're going to talk about delta H, the change in enthalpy, and the change in enthalpy is the same thing as Q, which is the heat of a reaction. I know, it's a lot to process, a lot of words that are almost the same, but not quite the same. How do we measure our changes in enthalpy, our heat, that energy that is transferred from a warm body to a cooler body? Kilojoules is our most common unit of energy in the metric system. For delta H, for Q, kilojoules. And again, that idea of kinetic energy is the energy of movement. We're going to add a couple little words just so that you know about them, but they're not going to be tested in SL. They are more higher level chemistry ideas. But sometimes what we're going to talk about today makes more sense if you at least know that these other ideas exist. So work is force that causes displacement in physics, but in chemistry, we're going to talk about this displacement that is related to changes in pressure or volume that are due to heat, that thermal energy transfer. For example, if I have some heat that is being supplied, there's RQ or delta H, to a system, the gases in this sample are going to have an increase in temperature. They're going to move faster, which is going to cause an increase in pressure and volume, which is going to cause this whole entire piston to rise. This is work done because we had a displacement. That displacement was caused by a force, that force related to changes in pressure and volume due to temperature changes, due to heat. We also have this idea of entropy. Entropy, or the letter S, is the distribution of matter and energy. The universe tends toward as much entropy as possible. We like to distribute matter and energy. We don't like to have things all hoarded up together. We don't like energy mashed up together. We don't like matter mashed up together. Things are more stable if they are more spread out. That is true for both matter and energy, and this high amount of spreading out or distribution is entropy. We use the letter S to describe entropy. Heat, or our change in enthalpy, can be either endothermic or exothermic. Endo is in and exo is out. We can have thermal energy being transferred from the surroundings to the system. the surroundings have more energy and the system has a little bit less energy, we can have that transfer into the system. That's going to be endothermic because we are adding energy to an endothermic reaction. Our delta H is going to be greater than 0. It's going to be positive. We have an increase in our enthalpy. Our change in enthalpy is positive. We've added more. Our exothermic reactions and exothermic physical changes are the opposite, where we're sending energy out of the system into the surroundings. So here our delta H, our change in enthalpy or our heat is going to be less than 0. It's going to be negative because there is a loss of energy from the system. It's going out to the surroundings. So the surroundings here are kind of endothermic because they're gaining the energy while the system is losing it. Super interesting. Our first law of thermodynamics says that there is a conservation of energy. So all the energy lost by the system is gained by the surroundings. Or in an endothermic reaction, all the energy that is being gained by the system must also be equal to what is lost from the surroundings. We can also represent endothermic and exothermic processes with some energy profiles. In our energy profiles, we are going to show potential energy on our y-axis. The x-axis is going to be the reaction progress or reaction coordinate, which is kind of like time, but it's not really time because we don't have equal increments of time. We're just kind of showing that it was like this and now it's like that. Time had to pass in order for the reaction to occur, but it is not equal increments of time. So we do not have time on the x-axis, even though time has passed. Reaction progress, reaction coordinate are what you're going to see as the label for that x-axis. So here let's look at this energy profile. Sometimes we also call these potential energy diagrams because we are showing potential energy on the y-axis. Here's the amount of potential energy that is stored in my reactants, and here is the amount of potential energy stored in my products. Chemical bonds store chemical energy. Notice that my reactants have less energy than the products, which means that we had to add some energy in order to make the bonds that are in the products. Because we're adding energy, our delta H, our change in enthalpy, is going to be positive. And because our delta H is positive, this reaction is endothermic. We're going from reactants up to more energy stored in the products. That makes it an endothermic reaction. The opposite is happening here in B. Notice that my reactants potential energy stored in the chemical bonds is here. Products is less. There's less energy stored in the products than there were stored in the reactants. That means that our change in enthalpy was negative. We went from here down to there. That's a loss of heat. That's a loss of enthalpy. And so our change in enthalpy is negative. This is an exothermic reaction. Let's talk a little bit more about these hills that we have between the reactants and the products. This increase in energy is the amount of energy needed to break the bonds in the reactants. So here we're having to add some heat. We're adding energy in order to break bonds. We're breaking the bonds of the reactants. This is the amount of energy needed to break the bonds of all the reactant molecules. We're going to call this the activation energy. Activation energy is the amount of energy needed to break the bonds in the reactant molecules. And then what happens is energy is released as our atoms go back together to make the molecules of the products. Because this here, where everything is like popped apart, super unstable. As those pieces and parts find each other and form new chemical bonds, we become more stable. More stable means less energy. So this decrease in potential energy is due to the formation of new bonds. Heat energy is leaving as these pieces and parts find each other and form new bonds. Bond breaking requires an input of energy. We're going to call it the activation energy. It's this increase right here. Bond making, when we make the new bonds in the product molecules, it's exothermic, and energy is going to be released as we make the new bonds that are in the product molecules. If we need more energy to break the bonds than we get back when we make the new bonds, then our reaction is endothermic. If, however, the amount of energy that we need to break the bonds is less than the amount of energy that is released when we make the new bonds, then our system is an exothermic reaction. One more little idea related to our energy profiles. The amount of energy stored in our reactants and products is relative to the stability of these molecules. The more energy something has, the more wiggly and jiggly it is, the less stable it is. The less energy something has, the less wiggly and jiggly it is, the more stable it is. So in this exothermic reaction, my reactants are less stable. My products are more stable because there's less energy, less wiggle and jiggle in those products, and so the products are more stable. We increased stability with our exothermic reaction. The opposite's happening in our endothermic reactions. Notice here that my reactants have less energy, my products have more. That means that the reactants are less wiggly and jiggly. That makes them more stable. My products are more wiggly and jiggly because they have more energy. That makes them less stable compared to the reactants. So we have a decrease in stability when we have an increase in energy. We have an increase in stability when we have a decrease in energy. Let's talk about some of the math related to energy changes, our changes in enthalpy thermodynamics. Our favorite equation for thermodynamics is going to be Q equals mc delta T, which is given to us in section 1 of our data booklets, some relevant equations. These are also all thermodynamics equations, but they are additional higher level content, so I'm only going to be talking about Q equals mc delta T. Q, or Q, is our heat, which is the same thing as our change in enthalpy. And sometimes we throw in this extra little theta to talk about how it is the standard enthalpy change. We are at standard temperature and pressure. M is going to be for mass. C is specific heat. And then delta T, of course, is going to be our change in temperature. Change in temperature is going to be final temperature minus initial temperature. Sometimes we get caught up in a, do I need to convert from Celsius to Kelvin in order to do my math here? For us in thermodynamics, it doesn't matter as long as your temperatures match. In gas law chemistry, friends, Kelvin, Kelvin, Kelvin every single time. Here, it doesn't really matter because we're looking at the temperature change. And what's super cool is because increments of Celsius and Kelvin are equal to each other, it doesn't matter whether we subtract in Celsius or Kelvin, because we're going to end up having the same difference. What? A same difference? Yes. Let's say that our final temperature is 0 degrees Celsius, but we started at 10 degrees Celsius. I'm going to subtract final temperature minus initial temperature. 0 minus 10 is going to give us a negative 10 degrees Celsius change. Our change in temperature is down 10 degrees. Because we started at 10, we went down to 0. TF minus TI, we had a negative 10 degrees Celsius change. What's super cool is that when I want to convert from 0 degrees Celsius to Kelvin, I'm going to add 273.15. If I convert from 10 degrees Celsius to Kelvin, I'm going to add 273.15, and I'm going to get 283.15. And if I subtract final minus initial, you know what I get? Negative 10 Kelvin. So our change in temperature in thermodynamics, and again, gas law chemistry, Kelvin, Kelvin, Kelvin. But here, it doesn't matter if we're in Celsius or Kelvin. The difference is the same, which is funny because difference and same are opposite. But in this case, friends, it is the same difference. Again, Q equals mc delta T. But what even is this thing C, specific heat capacity? It is the amount of energy required to change 1 gram of a substance by 1 degree Celsius or by 1 Kelvin. So here we have some specific heat capacities of some various substances. Notice that water down here has a quite high specific heat. The specific heat capacity of water is quite high because of hydrogen bonding. It's really hard for us to get water to increase in kinetic energy because the water molecules are stuck to each other with all those hydrogen bonds. So 4.1813 joules of energy are needed to change 1 gram of water by 1 Kelvin or 1 degree Celsius. Compare that to iron. To change 1 gram of iron by 1 degree Celsius, we need only 0.412 joules of energy. 10 times more energy is needed to change the temperature of 1 gram of water than is needed to change the temperature of 1 gram of iron. Notice, though, hydrogen gas. We need a lot of energy to heat up hydrogen and helium. Air, not quite as much as water. Steam, so gaseous water, actually doesn't need quite as much energy to change the temperature of compared to liquid water. And again, it's because of those hydrogen bonds that are holding those liquid water molecules to each other. So specific heat capacity, this is the amount of energy needed, usually in joules, sometimes in calories, but more often we're going to have it in joules, to change 1 gram of a substance by 1 degree Celsius, which is the same thing as 1 Kelvin. Most of the time, if you need any of these specific heat capacities for substances, they will be given to you in a problem, except for water. So the specific heat of water, the specific heat capacity of water is given to us in our data booklets, section 2, physical constants. So it is here 4.18 kilojoules per kilogram, which is the same thing as joules per gram. So if you've got kilograms of water, we're going to talk about the kilojoules of energy needed to raise the temperature by 1 Kelvin or 1 degree Celsius. If we have just grams of water, we're going to talk about joules of energy needed. Same number, just different units, different quantities of that water. Be careful with our C's because we also know that C is the speed of light. C is also our prefix for centi in the metric system. So just know, yes, there are more than one C. In this case, Q equals mc delta T. We're talking about specific heat capacity, the amount of energy needed to change 1 gram of a substance by 1 degree Celsius or 1 Kelvin. And hopefully you have your calculators ready because we are going to do some math with Q and delta H. Calculate the amount of energy in joules needed to raise the temperature of 10 grams of water from 12 degrees Celsius to 18 degrees Celsius. This is our mass, and this is going to give us our temperature change, where the temperature change is final minus initial. If this is my initial and this is my final, 18 minus 12 is going to give us 6 degrees Celsius. I want to calculate the amount of energy in joules. That's my Q, which is the same thing as Q. So let's figure out what equation we're going to use. Q and M and delta T. Of course, that's going to be Q equals mc delta T. Again, our M is 10 grams of water. Our C is given to us in our data booklet section 2, specific heat capacity of water. Since I have grams and joules, I'm going to use this version of the label, 4.18 joules per gram per Kelvin. We multiply that by delta T, our change in temperature, which we decided was 6 because 18 minus 12 is 6 degrees Celsius. Unit labels that are going to cancel out, I have grams on top and grams on bottom. They go away because degrees Celsius is the same thing as Kelvin. We're talking about the changes. Those also cancel out. So now with my handy dandy calculator, all we have to do is 10 times 4.18 times 6, and that's going to give us 250.8 joules. Let's do a quick sig fig check. I've got 2 sig figs and 2 and 2 and 3 sig figs. So I'm going to keep 2, 1, 2. My 0 isn't going to do anything to the 5. And so our final answer is going to be 250 joules of energy needed to raise the temperature of 10 grams of water from 12 degrees Celsius to 18 degrees Celsius. Let's do another one. This one's got a little bit more algebra for us to solve. Let's calculate the final temperature of 100 grams of water that have an initial temperature of 37 Celsius. If I've got 4.2 kilojoules of energy being lost from the water to the surroundings. So we're going to use Q equals MC delta T again, but what's interesting is that I've got Q and I've got M and I have TI, but I want to find TF. So we're still going to use Q equals MC delta T. My Q, 4.2 kilojoules of energy, is lost. The loss of energy, be careful here, is going to be negative 4.2 kilojoules of energy. I'm actually going to convert that to negative 4,200 joules since I've got grams here. We're going to set that equal to MC delta T. 100 grams is my M. Specific heat is still going to be my 4.18 joules per gram per Celsius, which is the same thing as Kelvin. And for now, I'm going to throw in a delta T. To solve for delta T, I'm going to divide both sides by 100 grams and 4.18 joules per gram per degree Celsius, which is the same thing as a change in Kelvin. Those cancel out. I'm left with delta T is going to equal, handy dandy calculator says that negative 4,200 divided by 100 and also divided by 4.18 gives us negative 10.0478, lots of digits. And this can be Kelvin, this can also be degrees Celsius because again the change is going to be the same. Let's make sure that this is actually degrees Celsius by looking at some of our unit labels. So joules top and bottom cancel out. These grams and these grams cancel out. What are we left with? Degrees Celsius in the denominator of the denominator, which puts it into the numerator. So next up, sig fig check. We need to do 2 or there is a decimal place in there, 3. We're going to keep 2. So I'm going to do 1, 2. That 0 doesn't do anything to that 0. So negative 10 degrees Celsius is my change in temperature. This is not my final temperature. It is my change in temperature. So negative 10 is my change in temperature. It is going to be equal to my final minus my initial. Negative 10 degrees Celsius is equal to final temperature minus my initial temperature was 37 degrees Celsius. To solve for final temperature, we're going to add 37 to both sides, which means that our final temperature is almost going to fit on the screen. Final temperature is going to be negative 10 plus 37 is going to give us 27 degrees Celsius is our final temperature. Let's look at another example problem, and here we're also going to start to talk about the equipment that we use to measure enthalpy changes. These devices, this guy and this guy, are known as calorimeters. Calorimeters. They're literally here for measuring calories. Calories are also units of energy. Even though we're using joules, we're not going to call them joulemeters. They're still calorimeters. We have these super amazing coffee cup calorimeters that are literally 2 styrofoam cups nestled inside each other to increase some insulation. We put a top on, we add our thermometer so that we can measure temperature changes inside our calorimeter, and then we've got a stir just to make sure that we don't have hot pockets or cold pockets that we're measuring. This guy is a little bit fancier. We do not have any of these in our lab at school. This is a bomb calorimeter. It literally explodes stuff. So you put your sample in here and then we pump a bunch of oxygen gas into it, and then these electrodes ignite the oxygen gas, and whatever we put into the chamber is going to explode, releasing energy. We're going to surround that inner chamber with water. And so there's lots of water here, and then this water is going to absorb the energy from the inner chamber, and we have a thermometer that is going to measure the temperature change of the water that is absorbing energy from our chamber. And again, we're going to have our stir just to make sure that we don't have hot pockets or cold pockets. We want to measure the average temperature of the whole entire solution surrounding the chamber. So bomb calorimeter, coffee cup calorimeter. Let's do a problem. Let's say that we added 1 gram of lithium chloride to a calorimeter. In our lab, it's going to look more like this. And in that calorimeter, we have 20 grams of pure water, and that water is starting at 25 degrees Celsius. As the lithium chloride dissolved, the temperature of the water rose to 33 degrees Celsius. We're going to try to figure out the molar enthalpy of dissolution of lithium chloride. We're going to do it in kilojoules per mole. We're going to start by figuring out the kilojoules of this, not a chemical change, but a physical change. As the lithium chloride dissolved, energy was released into the water. So let's actually do Q equals MC delta T. And we're going to do this not for the lithium chloride, but for the water. So the mass of the water was 20 grams. Specific heat of water is still at 4.18 joules per gram per Kelvin or degrees Celsius. And then the temperature change of our water, we went from 25 up to 33. So our final minus our initial is going to give us 8 degrees Celsius. It's our change in temperature. So our temperature units cancel out and our grams cancel out. We're left with joules. Let's figure out what is 20 times 4.18 times 8. Handy dandy calculator says that that is a positive 668.8 joules. This is how much energy was gained by the water. Where did all that energy come from that was gained by the water? It was lost from the lithium chloride. So Q of the lithium chloride is the same number, 668.8 joules. However, it's negative. This is weird. The water gained energy because the lithium chloride lost energy. The number is the same. All the energy that the water gained was lost by the lithium chloride. The numbers are the same, but because the water gained it, the lithium chloride lost it. So Q of the LiCl is negative 668.8 joules of energy for this 1 gram. But my question is asking me to figure it out in moles. So what I'm going to do now is convert my 1 gram of lithium chloride to moles of lithium chloride. Lithium is 6.94 plus chlorine is 35.45 on the handy-dandy periodic table. That is a sum of, 6.94 plus 35.45, 42.39 grams per 1 mole. That gives us calculator says 0.2359, lots more digits, moles of LiCl. So I want to find kilojoules per mole. So I'm going to take my joules and convert them to kilojoules by dividing by 1,000. That's moving my decimal place backwards 1, 2, 3 times. So negative 0.6688 kilojoules per 0.02359 moles. And when I do that division, we end up with 28.350996, so many digits, kilojoules per mole. So again, I'm going to figure out my joules, convert those to kilojoules. We're going to figure out our moles, and then we're going to divide kilojoules by mole, and that's going to give us kilojoules per mole. Sig fig check, and then we're done. We've got 1, 2, 3. We've got 1, 2, 3, 1, 2, 3. Ooh, only 1, 2 here, so we're going to keep only 2 sig figs in our final answer. I've got a 2 and an 8. That 3 doesn't do anything to that 8. So our final answer is going to be negative, I know I lost my negative there, negative 28 kilojoules per mole. Negative 28 kilojoules per mole. When lithium chloride dissolves in water, 1 mole of lithium chloride is going to lose. Lose makes it negative 28 kilojoules of energy. The molar enthalpy of dissolution, this just means dissolving, of lithium chloride is negative 28 kilojoules per mole. Hey, you guessed it, it's another practice problem. We've got 1 gram of granulated zinc reacting with 25 cubic centimeters of 1 mole per cubic decimeter copper 2 sulfate solution in a calorimeter. So let's go ahead and write our balanced equation. We have some zinc, that's Zn. We're adding it to copper 2 sulfate solution. Copper with a positive 2 charge, sulfate is SO4 with a minus 2 charge. Make sure you have those polyatomic ions memorized. Plus 2 minus 2 balances out, and so our formula for copper 2 sulfate is CuSO4. Ooh, I'm going to go ahead and throw my aqueous in there because that's going to be important. We're going to go ahead and react this in a single replacement reaction. We're going to get some copper. That'll be a solid, and what will be left is zinc sulfate solution. Luckily, zinc also is a positive 2 charge, which means that ZnSO4 is our formula, which means that our equation is already balanced. Yay! Let's figure out our limiting reactants. We're going to do that by converting all of our reactants to moles and then comparing to C, which has the smaller of the mole numbers. So I've got 1 gram of zinc. That 1 gram of zinc has a molar mass of 65.38 grams per mole. And so handy dandy calculator says that 1 divided by 65.38 is equal to 0.01529, lots of digits, moles of zinc. Let's do the same thing for our copper 2 sulfate. We have 25 cubic centimeters. We need to convert that to decimeters. We do that by dividing by 1,000, moving our decimal place backwards. 1, 2, 3. That turns our cm cubed into dm cubed. We're going to take that and we're going to multiply it by our molarity, which is 1 mole per cubic decimeter. Our decimeter positive 3 and decimeter negative 3 cancel out. We're left with moles, and that is going to be equal to 0.025 moles of copper 2 sulfate. So our limiting reactant, because all of our coefficients are 1, we can divide by 1, divide by 1. This is smaller. Zinc is our limiting reactant. And that's going to be pretty common when we are doing reactions with solutions in our calorimeters. We really want all of the solid to react. We want our solution to be in excess. So this is pretty common. Temperature change was recorded and graphed. We're going to figure out the temperature change of the reaction. Here's an interesting thing about graphing temperature. So we clearly don't have much temperature change here because I didn't add my zinc to my copper 2 sulfate yet. But then we did. And what happened was a pretty quick increase in temperature. And then as we're losing heat to our surroundings, the temperature is going to go back down. And eventually our temperature would crash until we get back to that initial temperature, which is probably the temperature of the room. Interestingly, even as the solution is gaining energy, we know that it's also losing energy. It's losing energy to the surroundings, even though we did this in a calorimeter because coffee cups are not that magical. We're losing heat to the surroundings even as we are propagating that heat in the reaction. So we are going to extrapolate the actual rise in temperature, actual temperature change, if there weren't any heat lost to the environment. So what we do is this. We're going to draw a vertical line from when we added that zinc. And then we're going to draw a straight line, a tangent, along the cooling of our solution as that solution is losing heat to the surroundings. We're going to draw it up until it runs into that vertical line that we drew from when we added our zinc. And then this point, not this point is going to be our final temperature. And so we're going to measure our temperature change as being 39 degrees Celsius minus 22 degrees Celsius. So temperature change, delta T, is going to be 39 minus 22. That's going to give us 17 degrees Celsius is our temperature change. Let's figure out the enthalpy change of the reaction now. We can do Q equals MC delta T. We're going to do this for the water. Where's the water? The water is what makes copper sulfate a solution. So our 0.025 moles of copper 2 sulfate are dissolved in water. That's what makes it an aqueous solution. So even though water is not part of the reaction, it's just the medium in which the copper 2 sulfate is being held, because the water absorbed the energy from the reaction between the zinc and the copper 2 sulfate, we're going to look at how much energy was absorbed by that water. Q equals MC delta T for our water. So that's going to be the mass of water. It's kind of the same as the mass of the solution. 25 cubic centimeters, that's not a mass, that's a volume, but the density of water at 22 degrees Celsius is 1 gram per cubic centimeter. So what does that mean if I have 25 cubic centimeters? We also have 25 grams of water. So I'm going to use 25 grams as my mass because our volume is 25 and the density of water is 1 gram per centimeter cubed. Specific heat of water is 4.18 joules per gram degrees Celsius. And then our change in temperature is 17 degrees Celsius. So now we have 25 times 4.18 times 17, and that's going to give us 1776.5 joules of energy absorbed by the water. If that much energy was absorbed by the water, that means that the reaction lost that much energy. Right? Are we so excited about the sign flip? Because the water in the calorimeter that dissolved the copper 2 sulfate gained energy, we know that the reaction itself actually lost energy. What? I know. So this is joules. Let's convert it to kilojoules. We're going to divide by 1,000. We have negative 1.7765 kilojoules of energy, but that's for a gram of zinc, and we want some molar enthalpy. We want to know how many moles that is. Luckily, I already converted my grams of zinc into moles of zinc. I'm going to use the moles of zinc because the zinc is our limiting reactant. Because zinc is our limiting reactant, we're going to go ahead and divide our kilojoules by those moles of our limiting reactant, 0.01529 moles of zinc. And then handy dandy calculator says that this is equal to negative 116.187, so many digits. Sig figs, we're going to keep 2. So 1, that 6 is going to turn that 1 into a 2. Our final answer, Q, is going to be negative 120 kilojoules per mole. This is our molar enthalpy of reaction. Let's talk about the many, many assumptions that we made in order to get to this answer. Number 1, we pretended like the density of water is the same as the density of copper 2 sulfate solution. They're not exactly the same. They're close, but not exactly the same. We also pretended like our solution's specific heat was the same as the specific heat for water. Similar, but not exactly the same. We're also assuming that all of the zinc reacted with all of the copper 2 sulfate. We're also assuming that all of the energy released by the reaction was absorbed by the water. probably in reality some was also released into the surroundings, because look at our graph. We know that some was released into the surroundings. So lots of assumptions made in order to do this math, but we did it anyhow. Hey, one more practice problem. This is the last one, I promise. We are almost done with this lecture video. So let's say that we're looking at the reaction between nitrogen gas and oxygen gas to produce nitrogen monoxide. So we've got 14 grams of nitrogen gas reacting with excess oxygen gas in a bomb calorimeter. I don't need to worry about which is my limiting reactant. We know that nitrogen gas is limiting. My bomb calorimeter has 100 grams of water. The temperature change of the water is recorded in table 1. Let's figure out the molar enthalpy of combustion reacting with oxygen gas for nitrogen gas. So Q equals mc delta T. One more time, we're going to find Q of the water in the calorimeter. So Q of the water, we had how much water? 100 grams of water. The C, specific heat of water, is still 4.18 joules per gram per Kelvin or degree Celsius. Our temperature change, we're going to use the table to figure that out. Our initial temperature was 22. The temperature went down, 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 and then it started to go back up, which means that this is going to be the lowest of our low temperatures. We're going to do initial and final. Final minus initial means that we had a negative 20 degree Celsius temperature change. So we're going to do 100 times 4.18 times negative 20. Q of the water is going to be negative, calculator says 8360 joules of energy. The water lost 8,360 joules of energy. Let's convert that to kilojoules. Divide by 123. That's 1 divided by 1,000. So we've got negative 8.36 kilojoules of energy is lost by the water. It was lost by the water because it was gained by the nitrogen gas when it reacted with the oxygen gas. So Q of our nitrogen gas is going to be a positive 8.36 kilojoules of energy per 14 grams of nitrogen gas. But of course, I don't want to do this in grams. I want to do it in moles. So let's take our 14 grams of nitrogen gas. We know that nitrogen gas is 14 times 2. That's 28 grams per mole. We had half a mole of nitrogen gas. So we're going to take our positive 8.36 kilojoules and divide it by 0.500 moles of nitrogen gas, and that is going to give us positive 16.72 kilojoules per mole. Let's do a sig fig check. I've got 3, I've got 4. We're going to keep 3, 1, 2, 3. That 2 does not change the 7. So our final answer, the molar enthalpy of combustion for nitrogen gas, is a positive 16.7 kilojoules per mole. And on that note, my friends, we have completed our video lecture on measuring enthalpy changes. We talked about what we can deduce from the temperature change that accompanies chemical and physical change. We can figure out the energy change, that change in enthalpy or heat. We looked at vocabulary. We talked about endothermic and exothermic. We looked at energy profiles. We talked about enthalpy of reaction and relative stability of reactants and products. Things that have more energy are less stable. Things that have less energy are more stable. And oh, so many Q equals mc delta T calculations. Great work today, my friends.